All right, now let's go ahead and take a look at a few debugging examples. We'll start off with a stop 133, which is a DPC watchdog violation. And then we'll take a look at a stop 9E, which is a user mode health monitor bug check. Well, let's go ahead and fire up the debugger, start it in administrative mode, and open up our crash dump. Here we go. And it gets loaded up into the debugger. So let's go back and take a look and see what we get so far. All right, first thing to notice is that we're running a Windows 10 kernel. This is build 14.393, so this is indeed Windows Server 2016 with 16 processors. As we go scrolling down through the information, we see it as a bug check 133. And then we get some warnings here about an unqualified symbol. Namely, it references something called tick periods. Occasionally, certain symbols will be referenced that aren't public OS symbols, and you get this sort of error. No big deal. Same with the page 3F00 not present in the dump file. Again, this will not hinder our analysis. But you can see here that the debugger says that the crash was probably caused by the vmbus.sys driver. This is for virtual machines. So this is obviously a Hyper-V host. So we'll start our analysis and we'll do the bang analyze -show command. As we can see, it is in fact a DPC watchdog violation, and it's telling us that argument 1 means that the system cumulatively spent an extended period of time at dispatch level or above. That's IRQL2. The offending component can usually be identified with a stack trace. Now, you may remember we took a look at another DPC watchdog violation crash, and its first argument was a 0, meaning that a particular device driver caused the watchdog to expire its timer. In this case, it's a cumulative time spent by the entire system, so it may not be just one driver to blame. So as we start out our analysis, we'll take a look at the current thread that was running. And as you can see, it is running a program called memtest64.exe. Well, it's also running at priority 17, which is real time. It's pretty high. So let's go ahead and take a look at the stack and see what it was executing. As you can see here, a system thread started up, and it was involving the balance set manager. Specifically, it was dealing with working sets. It was trying to trim or age. More specifically, it was trying to age working sets and then flush them out. That's what it's doing here. Then it got interrupted by this VM bus driver. A DPC was queued up, and essentially we got interrupted by the HAL timer clock, which notified us that we had essentially accumulated more ticks than we could, and it bug checked the system. So we can actually take a look at the instructions that were being executed at the time with the unassemble backward command. And you can see those various instructions, and we'll just show you a few more instructions. So you could see it was executing right about here when it put the stop code, the 133, into the ECX register and then called ntbugcheck. Now, I'll mention that the call instruction, the first thing it does is to push the return address on the stack so that when it returns from this call, that's where it would continue executing. Of course, we typically don't return from a bug check call because the system gets crashed. But I just wanted to show you that that's why we see this value on the stack, is because we executed a call instruction and it pushed the return address on the stack. So in any event, the mem test was running and we expired a timer which essentially said we were running too long at an elevated IRQL, so the system bug checked. So of Of course, this must be a memory-related problem with a process like memtest64 running, so let's go ahead and take a look at our memory utilization to see if that's a problem. So I'm going to issue the bang VM command, and we'll scroll back up here to take a look at the output. All right. So here we are, bang VM. The first thing it tells us about is the page file utilization. As you can see, the current size, the minimum, and the maximum are all different. So we're utilizing a system managed page file. Now, the thing I suggested you take a look at was the free space, which is approximately 7 gigabytes, and the current size, which is approximately 11 gigabytes. So you can see we definitely have at least 50% of our page file free. So that's a good thing. But if we look at our physical memory utilization, we can see out of 32 gig, only 636 KB is remaining. We are literally running on memory fumes. Well, that could be a problem. It's pretty concerning, but the fact that we have plenty of page file space says that we're not so desperate yet that we're dying or we crash because of a memory condition. So let's take a little bit more look around. If we cruise down here, we can see the various processes that are running that mem test. In fact, there are 4 processes, and they're each consuming about 3.6 gig of RAM. So if you start adding up those processes, and you can also see there's some other processes like this Tomcat that's using almost 2 gig. There's some Java processes out there, another Tomcat. So when you add up all those private bytes, you'll get total private bytes of about 22 gig. So combine that with the system overhead, that would explain where all your memory went. The 32 gig has effectively been consumed. So let's go ahead and take a little bit more of a look around, because I'm not convinced that we have a memory problem yet. So I'm going to do the bang running -it command, which, as you know, will show me all the different CPUs and what's running on them. So let's go back and take a look at exactly what was running. So on CPU 0, we can see that that's the CPU that bug checked, and that agrees with our debugger prompt. As you can see, the debugger prompt is 0. That means that's the crash CPU. We've already looked at this stack, namely it was doing some sort of aging of the working set and flushing it out. So let's see what the other processors were doing. Processor 1 was just running the idle loop. Processor 2 was doing some sort of lazy write scan, which means it was writing out pages to the page file. So CPU 3 was just running the idle loop, as was CPU 4. CPU 5 also in the idle loop, as is CPU 6. Now look at CPU 7. That had a thread running that is incurring a page fault at the time. So for some reason, maybe it didn't have the page in memory that it needed, or it was being kicked out. CPU 8 was running in the idle loop, as was CPU 9. CPU 10, however, was doing some sort of query working set information. CPU 11 was running the idle loop, as was CPU 12, 13. Now CPU 14 was incurring a page fault on a thread. And finally, CPU 15 was running idle. So as you can see, we've got quite a few idle CPUs, so we really haven't maxed out our processors. At least we don't appear to have. And the threads that were in fact running are all memory related, whether they're page faults or looking at the working sets or doing lazy writes. So there's certainly reason to believe there's a memory issue. But let's do a few more commands. We're going to do just the bang running command by itself without the IT, so you can get an idea of what that looks like. So as you can see here, we've got those 6 non-idle threads that are running. Here's the current thread on CPU 0 at priority 17, and this will be the very next thread slated to run on that particular CPU at priority 30. The same thing goes for the remaining CPUs, 2, 5, 7, 10, and 14. They all have their own threads running at priority 8 in this case, priority 0 on CPU 5, etc. So this is a good command just to see how many non-idle threads are running and at the various priorities. We're not really finding a whole bunch yet, so let's go ahead and explore a little bit more. So I'm going to issue that bang ready command that I mentioned. Okay, so let's go take a look at the output here. Here I issued the bang ready command, and as you can see right off the bat it says on processor 0 we have ready threads at priority 30. So we've got a thread that's ready to run at priority 30. We've got a thread that's ready to run at priority 15, one at priority 12, a couple at priority 9, and there's literally about 20 or more threads at priority 8 that are all ready to run on processor 0. But you see here that all the other processors, processors 1 through 15, have no threads in the ready state. So that's rather odd, because when the system creates a process and schedules the first thread, it'll put it on a CPU. The next thread it schedules, it'll put it on a different CPU because it tries to load balance these threads across multiple CPUs. But for some reason, all these threads appear to be running on CPU 0, and we're literally saturating it. So let's take a look at some of these threads. As you can see, there's a hyperlink here, so I can just touch this thread at priority 30 and see what it is. You can see that this thread is a system thread. This is the desktop window manager thread, and it runs at priority 30. So it's going to be getting the CPU's attention before any other threads out there. Let's see what else we have. We've got thread right here running at ready at priority 15, and that's an SVC host type process, another system process. Let's take a look at a couple more here. We've got a thread ready to run at priority 12. If we look at that thread, it's an image called bit.exe. All right, and as we noted, it's running at priority 12. And we can see what it's doing on its stack. It's doing some sort of set information about the process, and then it's doing a set affinity. Well, let me explain something here. It is possible to set what's known as the affinity mask so that a process and thread only runs on a particular CPU. And that would be noted here by its ideal processor. That's where it would like to run, on processor 0. So it seems as though this bit.exe process is indeed establishing all the threads to run on CPU 0. So let's take a look at a few more of those threads. Here we've got a couple running at priority 9. If we look at that first one at 9, it's just the bit.exe again, another thread in there, and it's doing some sort of wait for multiple objects. So it's just waiting. Let's go ahead and take a look at that other thread at priority 9. Here we go, right here. And let's see what it was doing. It is also this bit.exe program, whatever it is. And you can see that it's doing some sort of read file type function through NTFS. In fact, this thread has an outstanding IO request packet. So we could take a look at that IO request packet with the bang IRP command, and we can see that indeed there is a object here associated with that IRP, and we can use the bang object command to figure out what it was doing. And you could see that it was actually accessing a file called burn-in-test. So that gives us a pretty good idea of what this bit.exe thread is running. It's running a burn-in test. Okay, so things get a little bit more interesting now. So let's go back to that bang ready command. And we know that we've got the burn in test thread doing a lot of different stuff. And if you look at all these threads at priority 8, a lot of them have very close to the same TEB, which is the thread environment block. And I've gone ahead and looked at all these, and these threads are all the BIT type threads. So let's take a look at a few of them running at priority 8 to see what they're doing. So I just tap on this hyperlink, and you can see once again it's the BIT program that's running, and look what it's doing. It was running in user space, and then all of a sudden it fired off a DPC, which is a deferred procedure call. These are very CPU intensive. And if we were to look at several of the other threads, I just pick one at random, and you'll see that it is doing the exact same thing. It's firing off all these DPCs. Again, very CPU intensive. The question is, why do we have all these threads ready to run on CPU 0, and we know that they're purposefully being run on CPU 0? So a final check we can do is there's a debugger command called bang DPCs. This will show us all the DPCs that have been queued out there across the different processors. And if I issue that command, you can see that on CPU 0, we have numerous DPCs that are all in a queue, ready to be executed. There's various ones like from the store port driver. This is very important stuff that needs to get done in a timely fashion. There's the NDIS driver. There's some other drivers out there. The fact of the matter is, we've got this CPU 0 that is so saturated at this point with all these ready threads and DPCs that it's not getting the time of day to do anything much. And that's why we expired that WATCHDOG timer. Not because we ran out of physical memory, but because we saturated CPU 0 so much that it couldn't get to the various drivers in time, and that's why eventually we incurred this DPC watchdog violation. It's not to say that those low memory conditions didn't exacerbate the problem, but the fact of the matter is this application was doing burn-in testing, trying to saturate CPU 0, and it really accomplished that, and that's why the system bug checked.